All right, here is our first main video for 3.1 for chapter 3. The quick version of what a determinant is it's how big the columns of a matrix are. We are only talking about square matrices, by the way. But specifically, like if you have a matrix like this, all three of these columns point in different directions. They're all linearly independent from each other, and they're also big vectors. They're 100 units long. So this is, in a sense, a big matrix. But if you had something a little different, like if in the middle column this was 200, 0, 0, then suddenly the second column isn't really doing anything. And now this is what we're going to think of as a very small matrix because it doesn't, the three vectors don't actually point in different directions, even though the numbers are big. So it turns out this is going to have determinant equal to 0. So the determinant's going to be a number, and it's also going to turn out that the one we had previously before I erased it has determinant 1 million. And yeah, we're going to see why the determinant is not 0 if and only if your matrix is invertible. So chapter 2 is going to play a big role here. We're going to see how the determinant tells you about something like the area of a parallelogram or the volume of a parallelepiped, like you just did in the warm-ups. And the determinant also tells you about what happens when you multiply other vectors and matrices by A. Like how much does multiplying A stretch out other things? And that's really important in a lot of applications of linear algebra, like in multivariable calculus, and all the places where you do like flux integrals and physics and all of those kinds of two-dimensional and three-dimensional integrals. Determinants play a big role there. Not just physics, but I'm sure they do a lot of that in other kinds of engineering and statistics. So it turns out the formula for the determinant of A is pretty complicated. And the way we're going to do it in this book is we're going to do it really backwards from a traditional way. I got this from an excellent book called Linear Algebra Done Wrong by Sergey Trail. By the way, there's another book called Linear Algebra Done Right that came out before, and Sergey Trail was like, I'm going to do the opposite of that book. And it's not like one is really right and one is wrong, they're just different. But it's a good book, and I like the way he does determinants. So we're going to do the same thing here. So yeah, hopefully you already went over the warm up, so you know about how the area of a parallelogram works a little bit. But we're also going to talk about three-dimensional parallelograms, aka parallelepipeds. And here's a picture of a parallelepiped. We've got the origin right here and these three arrows pointing in different directions. And all of the faces, like for example, this face here in the front, that is the parallelogram determined by A1 and A3. And this face over here is the parallelogram determined by A2 and A3. So all six of the faces are parallelograms like that. Now to get the volume of this, you would take the area of the base. Let's say the base is this one on the bottom. That's going to be the length of that times the width. And that width is drawn in a way that makes it perpendicular to the A1 vector. So that's just a regular parallelogram. But then to get the volume of that, well, it's like how far do you go into the third dimension perpendicular to that to get the volume? And that's going to be the area of that base times the height here. And that also needs to be perpendicular to the other side. So we could talk about the volume of hyperparallelepipeds in 4 or 10 dimensions or things like that. And those things do have applications in mathematics and in statistics and physics, even if you can't draw a picture of it. But it's hard to talk about what we even mean by volume of those things and what does perpendicular mean exactly. We can't draw pictures of it. So we're still going to write these things as like parallelogram A, like that. Even if A is like a 5 by 5 matrix and we're talking about a 5-dimensional hyperparallelepiped. And the 5-dimensional volume of that, we're going to use the same term as the volume of a 3-dimensional parallelepiped and the same term for the area of a parallelogram. All of these things are called volume. So, in order to define what this is, like the goal here is to make the volume of any parallelepiped parallelogram thing in any number of dimensions, we're going to make up a formula for something called the determinant that tells you that thing. But in order to do that, we're not going to do it in terms of like perpendicularness exactly. We're going to define properties that volume should have that are consistent with R2 and R3. And that's going to be our definition for like 10-dimensional volume as well. Okay, now a determinant is a function whose domain is the set of all square matrices and whose codomain is R. So you plug in a matrix and you get a number. That number represents the volume of the parallelogram thing. And we want it to satisfy all of these properties. And we're going to go through with some pictures about why these are consistent with volume. Oh, I should point out that a matrix is basically the same thing as a list of its column vectors. So sometimes we'll write it as the determinant of a list of vectors, and that's just another way of saying the determinant of that matrix that has those vectors. Anyways, first of all, normality, which is that if you get the determinant of the identity, the result should be 1. So, for example, the volume of this square, it really means area because we're in R2, but it is 1 times 1, which is 1. So that's why the determinant is 1 here. Likewise, in R3, now volume really does mean volume. So this is a cube with side lengths 1, 1, and 1 everywhere. So the determinant of this matrix should be equal to 1 times 1 times 1 as well. So that's like the basic kind of parallelogram that we're going to relate other kinds of parallelograms to, or parallelepiped. Now, another property, the next property that we should have, the scaling type of linearity, is multiplying one column by a scalar also scales the determinant. So, like, if you were to take this AJ column and replace it with K times AJ, the result over here is K times bigger. The volume of that thing is K times bigger. You saw an example of that in warm-up number B or D, whatever this one is here, when you replaced one of the columns by 1/2 times the other one, the whole thing got scaled down by 1/2 and the area was half of what it was before. Yeah, we also have like a picture of this here. So yeah, the volume of a parallelogram that has one side that's twice as big as the unit square is 2, which is 2 times 1. Okay. Now, a thing to point out is this allows for determinants to be negative. Notice that the section was called signed volume. What the heck do you mean by that? Well, I mean the volume that can be negative. So if you were to take the unit square here and with one of its vectors there and replace that with negative 2e1 here, then the signed volume of this list of vectors is going to be -2. Now, I know that's a little different than like just the concept of the area of this rectangle, which is clearly 2. So why are we calling it -2? Well, having this property allows a concept of determinant to have a linearity property. Like, in calculus, when you think of a single dimensional integral as like the area under a curve, but if the curve is below the x-axis, it becomes negative. This property that when you scale a function by c and do the integral, you get the same thing as c times that integral. That makes doing integrals a lot easier, right? So the same is true with determinants. We want to have that property for determinants too. Now, it does turn out that the sign of a 2 by 2 determinant, whether it's positive or negative, depends on whether you turn counterclockwise or clockwise to get from the first column to the second. So, like, here's the first vector is -2e1. To go from there to the second vector, you have to turn clockwise. That's like a -90-degree angle, right? If you think about the standard way that like, positive 90 degrees would be if you went counterclockwise. So yeah, if going from the first one to the second, you have to go by a negative angle, that's going to give you a negative determinant. It also means that if you do the determinant of these written the other way around, well, it's not exactly the same matrix, even if it represents the same rectangle. But anyways, this determinant is actually going to be +2. Next, let's look at linearity with addition. Now, the determinant distributes over vector addition in any one column. So, like, if you have a column that is the sum of these two columns, you can basically distribute the whole rest of the determinant over that. This one might look a little weird, maybe not as obvious as the other ones, but here's a picture of it. So let's say that this is A1 and A2 here. The determinant of this is 2. And here's another parallelogram that has the same A1, it's just that the B2 is different. And the area of this one is going to be the same base of 2 times the height of 2. Now, what if we make a new parallelogram, or we could say a new matrix with the same column A1 as before, but the second column is A2 plus B2? And what is the height from the same base up to the opposite side? Well, it's 3, because when we added these two vectors together, it's like we're also adding up how far away they are from the base A1. So that's why you should expect the volume of the result to be equal to the volume of the two smaller parts. All right, let's look at another kind of more complicated one. Preservation under column multata placement, which says replacing one column with the sum of itself and a scalar multiple of a different column does not change the determinant. Now, it really has to be a different column, just like you have to do it with a different row when you're doing the row operation. So this determinant is going to be equal to this other determinant. Now, why is that? That might be a little surprising. So here is A1 and A2. A2 is the diagonal one, and A1 is the horizontal one. Now, if you replace A2 with the sum of itself and a different one, what you're doing is you're like moving this vector parallel to the other vector. This doesn't move the new vector any farther away from B than it was before. Here's a 3 by 3 example. So like if you want to find the volume of this parallelepiped, we could turn it into a rectangle by replacing some of the vectors with linear combinations of themselves and other vectors in the list. So like for example, if you want to get a nice right angle here to make a rectangle, we could just move A3 in the direction of A1. And that doesn't change the height because we're moving the point in a direction parallel to the bottom. Okay. And likewise, you could do the same thing with A2. Moving A2 in this direction is not changing the width. It's not changing the distance from the A1 side perpendicular to the A1 side to over here because we're just moving it in a direction parallel to the A1 side. So this is like a more complicated version of taking a deck of cards and leaning it over to one side to change it from a parallelogram to a rectangle. So yeah, it turns out all of these properties give you a good way to define volume in R2 and R3 and R27 or whatever you want. Now, eventually we want to like know how can you actually take the matrix itself with the numbers in it and calculate the determinant, calculate the signed volume of the parallelepiped that it makes. And in order to do that, we've got to prove some theorems, and we're also just going to practice calculating the volume of things using these rules. But we'll do that in the next video.